All right, back from break. Who knows how long that break was? Let's see. So we're back to looking at energy in a simple harmonic oscillator. This thing is oscillating back and forth. And what they say is, what happens if we double the amplitude? So we pull the object back twice as far. How much energy would that correspond to? And then also what would happen to the maximum velocity, the maximum acceleration if we double the amplitude? Now, let's think about this. What we've said with these oscillating systems that we've looked at so far, kind of these ideal simple harmonic oscillating systems, is that the period doesn't depend on the amplitude. Let's go back and see if we can track that down somewhere. I guess that's really right back at the beginning, huh? So what we can say then is that the frequency depends on the K value. Frequency depends on the K value, and it depends on the mass. And so if I change the amplitude, if I have a small amplitude, and if I have twice the amplitude, or if I have 10 times the amplitude, the frequency doesn't change. That doesn't affect the frequency. How can this oscillating system travel twice as far, 10 times as far in the same amount of time, and it has to go twice as fast, or 10 times as fast? So that's kind of an interesting property of simple harmonic motion. The frequency itself depends on the K value, and it depends on the amplitude, but it doesn't, it depends on the K value and the mass, but it doesn't depend on the amplitude. It does not. And so if we double the amplitude, what's going to happen to everything? And what we find is, the energy of oscillation is 1/2 Ka squared. Well, if I double the amplitude, that factor of 2 will get doubled. That's going to be 4 times the energy. So twice the amplitude represents 4 times the energy. Vmax, oh, here we go. It was right here the whole time. The frequency is given by K over M square root. So we do have it, it's set up here. So K is a constant, M is a constant, omega is a constant, and it doesn't depend on what the amplitude will be. So amplitude doubling will not affect the frequency. Frequency will stay the same. What does that say about Vmax? Well, Vmax depends on the amplitude, which is going to double, but the omega is unaffected. So the Vmax also will go up by a factor of 2, and for the very same reason, the acceleration max will also go up by a factor of 2. So it's like what we were talking about. If we double the amplitude, everything happens twice as fast. So the periods end up taking the same amount of time. The velocities double, the accelerations double at each location in the cycle. Is that a good way to say it? In terms of time, at each instant, time instant in the cycle, not position, but in terms of time, everything doubles. It goes twice as fast, the accelerations are twice as large. 4 times the energy. All right, here the book has this short section in it showing that we've been using omega to represent how fast something oscillates back and forth. Earlier, back in chapters, in chapter 10, we used omega to keep track of how fast something was rotating. And here what we're showing is rotation and oscillation are very closely related mathematically. So if I have something rotating with uniform rotational speed, omega, if I do the, here's the object going around in a circle. If I look at the x projection, that's a cosine function. So the x component of that is a cosine function that's oscillating. The y component is a sine function. So from a circle, you can separate out x and y projected motion, and those are sines and cosines. So there is this relationship between rotation and simple harmonic motion. All right, we want to move on and look at some other oscillating systems. Up until now, we've kept saying, here's a spring, here's a mass, here's a spring, here's a mass, pretty much every example. Now what we want to do is, let's do something crazy. Let's look at a pendulum. So here's a pendulum, and the pendulum is oscillating back and forth. Now, we looked at a pendulum back when we were doing energy calculations, energy conservation, chapter 8 maybe, something like that, 7 or 8. Well, here's the pendulum again, and we know that a pendulum oscillates. Is the oscillation simple harmonic motion? So let's take a look and see. In order to have the oscillation be simple harmonic motion, the restoring force would need to be proportional to the displacement. So that would say that the restoring force here, from this diagram, is mg sine theta. So the restoring force that's bringing the pendulum back to the equilibrium point is the sine theta component of gravity. So here's gravity here. Now, the distance, x, represents how far we are from equilibrium, and x is along a circular path. X is actually a circular arc. And so x would be equal to L times theta. So let's see how that plays out. Here's my drawing. Here's the gravitational force. Here is mg sine theta. Here is mg cosine. I guess I didn't bother to get the tension. I should have put it in there. Put the tension inside here. Here's where the equilibrium is. Now, the way simple harmonic motion works is that I need a restoring force that's directly proportional to displacement. That says that the k value, the force constant, needs to be the absolute magnitude of the force divided by the absolute magnitude of the displacement at that location. Now, the restoring force is mg sine theta. The displacement, x, is L theta. So when I plug those into this formula to determine the force constant, the sine theta and theta, they don't cancel. So I need those to drop out, because if I'm going to have simple harmonic motion, k needs to be a constant. Now, one thing we should also talk about here is, isn't k a spring constant? And it has been. Up until now, we've been using the little k to represent the stiffness of a spring, but now we're going to generalize its meaning. Now what we can say is, any situation with a restoring force as a function of displacement, I can calculate k by taking the restoring force formula, dividing through by the displacement, and if that works out to be a constant, then it's simple harmonic motion. If it's not a constant, well, it's still oscillatory, but it's not going to be exactly sines and cosines. It'll be some other functions, some combination of sines and cosines and other cosines. This isn't quite constant. It's not quite simple harmonic motion, unless we keep the oscillations really small. In the limit where theta is small, sine theta and theta have almost the same value. Now, that might sound like a surprise to you, but let's take a look and see how that works. This is what we are thinking when we use a small angle approximation. Now, let's take an angle of 5 degrees. That seems pretty small. First I have to convert that into radians. So 5 degrees in radians is 0.0873. If I take the sine of 5 degrees, I get 0.0872. If I take the difference between those numbers, theta and sine, theta measured in radians, which is whenever we have a formula with theta by itself, that's in radians. And so these are the numbers that we're comparing. So this is theta in radians, this is the sine of theta. They differ by 0.1%. At 10 degrees, the number of radians is 0.1745. The sine of 10 degrees is 0.1736. That's about a 0.5% difference. By the time we get to 15%, we're still within one, well, not within, but just barely beyond 1% difference. But then it grows. At 20%, it's up to 20 degrees, it's up to a 2% difference, and as the angles go up, it becomes pretty significant. And so if we keep the angles down around 5 or even 10 degrees, we're going to be very accurate. It's still not exactly simple harmonic motion, but it's pretty close. So for that, what we do is we say sine theta is approximately theta, and we cancel these out, and we say that there is a force constant given by mg over L. So that's our analysis for simple harmonic motion, or roughly simple harmonic motion in a pendulum. So that's what we've listed here. The force is roughly proportional to mg over L times x. That's our k value, the k expression. And x is equal to L times theta. Now, that says that, well, the frequency, 1 over 2 pi g over L, the period is here. I hope I don't. I do. Okay, here we are. So here is a pendulum. Once again, we're using it to measure gravitational field. So let me go back and pick up these slides that we kind of skipped. I want to come back and be more clear where these formulas are coming from. I feel like they've just kind of grabbed those out of thin air. Here's a simple pendulum. Here is a chandelier light fixture inside a cathedral. If this is oscillating back and forth slowly with a small angle, which it would, then the period of oscillations, it's simple harmonic motion, and the period of oscillations won't depend on the mass. Now there's kind of a story about Galileo, that when Galileo went to church, that he wasn't really listening. Instead, he would watch the chandeliers go back and forth. There would be a breeze coming through the windows, and the chandelier might be oscillating back and forth a bit, and he would use his pulse to time the oscillations. And what he found was the small amplitudes and the larger amplitudes would have the same period. So that was interesting to him. So he was kind of mapping out these properties of simple harmonic motion. And of course the angles were small, so the chandeliers were not oscillating with very large angles. So here it says that a geologist has taken along a portable pendulum system and using it to measure the gravitational acceleration at a point along the Earth's surface. So here's the pendulum, same thing we saw before. Now I'm going to repeat a lot of the same stuff. For the pendulum, the restoring force, ooh look, I even wrote the tension in. The restoring force is mg sine theta. The distance traveled from equilibrium is L times theta. That gives us a force constant that is mg sine theta over L theta. For small angles, we can cancel the sine theta and theta. That gives us mg over L. Here's the final step that I didn't include before. Omega is given by the force constant divided by mass. and we square root that. Well, when I substitute in mg over L and divide through by the masses cancel out. And so the frequency of oscillation for a pendulum depends on the gravitational field and the length of the pendulum. And then we take a square root. But it ends up being independent, or at least we predict, it's independent of the mass. So the frequency is going to be g over L square root. That means I can solve for g. So this geologist took a pendulum device along with, along on the trip, and g is equal to L times omega squared. That gives us L 2 pi f squared. So the g value, 4 pi squared, L f squared, that's 4 pi squared. The length, they told us, was very precisely measured to 37.10 centimeters. That's hard to do. We'll talk about that a bit. And then the frequency was measured to be 0.8190 per second. Now, putting all those numbers together, we ended up with a gravitational field, or gravitational acceleration, 982.4 centimeters per second squared. Now, compare that to 980, that's coming in pretty close. So maybe the geologist is working in an area where the gravitational field is a little larger, or maybe it's just a latitude effect, right? At different latitudes we'll measure, G will come out anomalously because of the rotation of the Earth. Let's see. Oh yeah, so we were measuring this to 4 significant figures because this was in 4 significant figures, and so was this. Now, the formula we're using is for a simple pendulum. So this formula we're using only works if the amplitudes are small, right? Now, we saw even at 5 degrees, the periods are going to be off by 1 part in 1,000. So that sounds like 3 or 4 significant figures. That's kind of a limit. And then the pendulum itself, how do we measure something, the length, so accurately? That has to be measured from here, right down to where the mass is located. And the mass needs to be small and compact. And the length, the string along the length, cannot have any mass. That's a problem. So the simple pendulum, the model is too simple, probably. We have to have an attachment here, whatever that is. Maybe it's a very thin rod. Has to be really small compared with the mass down here. So my guess is if they use these pendulums, they probably have to be calibrated somehow in a known gravitational field in order to be useful. Anyway, that's my guess as to how we would do these measurements. Okay, what other kind of oscillating systems can we come up with here? And we could oscillate a baseball bat, right? So the idea here is, now these are called a physical pendulum compared with a simple pendulum. A physical pendulum is anything you want. It could be a baseball bat. What you do is you get any object you want, you drill a hole in it wherever you want, you identify where the center of mass or the center of gravity is, and you measure the distance between where the center of gravity is and where the where the axis of rotation is. So here's the axis of rotation, here is the center of mass, and this baseball bat then, we put an axis right here, we put some kind of an axle, and we let the baseball bat oscillate back and forth. Now, as the baseball bat oscillates back and forth, it's going to, well, I guess the question is, will this be simple harmonic motion? And if so, how do we determine the period? Because now, instead of the pendulum being simple, the pendulum has mass spread all over the place. It's still a pendulum. So what we do now is, let me jump ahead. We'll come back here if we need to for their nice picture. But let me set up a force diagram. So let's say that we have something that looks like a a physical pendulum, and this one doesn't look like so much like a baseball bat, but there is a gravitational force. The gravitational force can be placed as if it's all coming from the center of mass. So we'll take that gravitational force and place it at the center of mass. Here's the axis. We measure this distance h. The restoring force is mg sine theta. But rather than thinking in terms of a restoring force, we're going to think of it a restoring torque. Now the restoring torque is going to be mg sine theta times h. So h now is a lever distance. The angular displacement is theta. So what we've done, instead of working at f and x, linear displacements and forces, we're going to use torques and angular displacements. Now it works out that we can define a torque constant, where the torque constant, and for this I'm using a big K, I'm using a Greek kappa. Let's see, this is torque divided by theta, similar as to before. So the torque constant will be mg sine theta times h over theta, and again, we'll limit this to small angle. So let's say, okay, we promise we're never going to let this thing oscillate with a large angle. We'll keep it down below 5 degrees, something like that. And we go, okay, then you have permission to go ahead and cancel out the sine theta and the theta. So those go away. It says that the torque constant for my physical pendulum will be mgh, where m is the mass, g is the gravitational field, and h is the distance between the center of mass and the axis of rotation. So it's the axis of oscillation, let's call it. Now, to further move along this analogy, the frequency of oscillations we can show is given by the torque constant divided by the rotational inertia. So we're using the very same formulas, except all the linear quantities have been replaced with rotational quantities. And so that tells us that the frequency of oscillations will be mgh divided by I square root, and we have to stick with a small angle. That's the agreement. So that's the formula that is going to work. So if we come back up here, we're good. I mean, you can take a look at the picture here. I like the baseball bat oscillating back and forth. That's a pretty good idea. But these are the formulas I'm going to say are the easiest to work from. All right, so let's continue with this. So what we'll say then is that there's an acceleration that is given by the torque divided by the rotational inertia. The torque is going to be mg sine theta times h over I. That's roughly given by minus mgh I over theta. If we take the second time derivative of that function, what we're going to get is minus mgh over I times theta. Let's see how this works then. Let's use cosines. We'll say that the oscillations then can be represented as amplitude. Now notice, now the amplitude is in terms of degrees. So some number of degrees of amplitude, theta naught, times the cosine of omega t. That makes the velocity, the angular velocity, the rate at which it oscillates back and forth. Now that's not the same thing as omega. That is that's an oscillatory frequency. So this is actually an angular velocity as the object, how fast is it moving back and forth. And this is the angular acceleration. So omega is doing kind of double duty here. That's dangerous. In any case, the omega squared is k over I. So this establishes, I hope, that we can apply this for a physical pendulum. Okay, and here's all the formulas they have. I'm not so worried about these. Here we go. I'm more interested in this. So here is the example. The distance between the axis and the center of mass is 42 centimeters. That's h. And it's a 1 kilogram stick that is non-uniform. It can be balanced at a point 42 centimeters from the end. The oscillation period is 1.6. Okay, let's go in and calculate. What they want us to calculate is what's the moment of inertia for this stick. So let's do this. Here is the axis. Here is the center of mass. That's h. The k value will be given by mgh. The omega is given by k over I. So here's how we're going to calculate the rotational inertia. We can calculate it as the torque constant divided by omega squared. Now, h is 42 centimeters. The period is 1.6 seconds. That means the frequency is the inverse, that's 0.625, and omega is 3.927 radians per second. Now, the mass is, so we've got the frequency, we got the frequency from using the period that they gave us. Now what we need to do is come up with the k value. The k value will be given by mgh. This is m, this is g, this is h, this is k. So the k value is going to be 4.116, the torque constant, newtons per meter. If I follow this formula, so I'm going to take k and divide through by 3.927 radians per second squared. Now, the seconds will remain, but the radians we can just drop. So we'll just drop the radians, and that leaves us at 0.267 kilograms times meters squared as the rotational inertia. So we've actually been able to use this pendulum to determine the rotational inertia of an object, of a baseball bat. Now, the rotational inertia that we've calculated specifically applies to this point on the end. What would be the rotational inertia around the center of mass? And it is going to be less, right? We know that the rotational inertia around the center of mass is going to be less. And we can figure out by how much using the parallel axis theorem. So let's bring out the parallel axis theorem. It says that the rotational inertia at the end is equal to the rotational inertia around the center of mass plus m times h squared. Now let's flip the equation around because we have measured the rotational inertia around the axis. So let's calculate the rotational inertia around the center of mass. And that's going to come by taking this rotational inertia around the axis, 0.669 kilograms meters squared, and subtracting off mh squared. So minus 0.1764. And look, the rotational inertia went down by about a factor of 3. The rotational inertia around the center of mass much lower than the rotational inertia around one of the ends. All right. Questions on that? All right. This oscillation can also be set up in terms of what's called a torsional pendulum, and that's a wire that twists. So it can twist back and forth. We can define a torsional constant for the wire and work in terms of a rotational inertia for this one also. So different types of oscillating systems, different types of pendulum, I guess. These are all kind of related to that. All right, we wanted to get to this, so we're finally here. What happens when we have damping taking place? So what we've got here is, let's say we're back to having a spring and a mass, and but in this case, there's a resistive force. Something is opposing the motion of the oscillating object, and so as a result, the amplitudes are decreasing with time. So the amplitudes little by little, or a lot by a lot, are dropping off. What we're expecting then, a more realistic picture, would be an amplitude that drops off with time as the system oscillates. So we're going to introduce a damping force. So we're going to say that as the object oscillates back and forth, we are going to have a force that opposes the velocity. Let me see if I've got a diagram. There we go. So here what we're going to have is, here's the mass, here is K. There is a force coming from the spring, which is negative Kx. And negative means that the force and the displacement will always be in opposite directions. The force is always going to be opposite to the displacement. Now, we're going to add in what we call a damping force. And damping forces are opposite the velocity. Now, we're going to say it's directly proportional. That's a bit of an idealization. So this is an ideal spring. This is an ideal damping effect. And the negative sign here says that the force is always opposite to the velocity. Now, this can be a conservative force, but this is not. That's going to start taking energy out of the system, and the amplitudes will get smaller. So we start off by saying the acceleration of this object is equal to the F net divided by m. And the two forces that are acting on it is the force of the spring and the damping force. That gets divided by m. We can write that as ma plus bv plus ka equals 0. Now this is a force, this is a force, this is the acceleration term. But we've written it in a way where now we can substitute for the a, we can say that's the second time derivative, the velocity is the first time derivative of displacement, and displacement is displacement. Now in this formula, this is to impress your friends. You can show your friends this is what we're learning in physics. This is what's referred to as a differential equation. And no, you don't have to take a differential equation class to complete this course. It turns out m, b, and k are all constants. X of t is a function. So when we solve this, notice how we skipped all the steps. When we solve this, the solution that we end up, one of the possible solutions, is an oscillating system where the amplitude drops off exponentially. And that's the same thing they've shown. So they jumped kind of quickly to right here and then said this is the solution. Now the rate, the constant here, the rate at which the amplitude is dropping off, that gamma constant is given by b over 2m, where m is the mass and b is the damping constant. So if I have a large damping constant, the amplitude drops off very rapidly. Now I can compensate for that by putting a lot of mass in the system. So a lot of mass pushes its way through. That's a lot of inertia. It's harder to bring an object with a lot of mass, slow it down and stop it, compared with something with not much mass. So it's an inertial effect that we're seeing. Now what you also might ask is, well, if this thing starts to oscillate, will it oscillate with the same frequency as before? Or will it have its own different frequency? And it does turn out that a damping constant reduces the frequency. And it reduces it by the amount given by that formula. So that formula is telling the amount that the frequency it'll slow down. The oscillations will take a little longer. The periods are going to be a little longer than they were before. But not necessarily by a lot. What we find is if you add a lot of damping, then the amplitudes can drop down pretty quickly. in most cases with the pendulum, where the pendulum's oscillating back and forth many, many times, there's not much damping. If something's oscillating back and forth at least several times before it slows down and stops, there's not much of a damping effect going on there, actually. Okay, there's not much of let me say this, there's not much of an effect on the frequency. So the effect on the frequency is pretty small. All right, so we caught up with this slide. So that's the solution that we're looking at. Now, the solution that they've given us, okay, here is a solution that they've given us in the textbook, and I've written that down. And you guys aren't, you don't have to derive this. This is just so you can see how some of the mathematics plays out when we do have damping taking place. Now, it turns out this function is not ideal in some sense, and the idea is it would be nice to have a function where if we pull the pendulum back or we compress the spring and let go, that at t equals 0, we are at the maximum amplitude and the velocity is 0. It turns out this function, when t is equal to 0, we are at amplitude, x equals a, because when t equals to 0, well, the cosine goes to 1, and when t equals 0 here, the exponential goes to 1. So that function says x equals a at t equals 0. But when we take a derivative of that to get the velocity, we find out that this function does not provide us a velocity that's 0 initially. So we can take a closer look. Now, again, I'm not going to go through all the details, but if we go back to this solution, what we can do is, or back to this equation, what we can do is use a more general solution. Instead of using just a cosine with some kind of an amplitude, we can add on a little bit of sine. Now, that doesn't change the initial starting point so much, because at t equals 0, this drops out anyway. So this function still has the property that when t is equal to 0, this all drops out. When this is equal to 0, this becomes 1, this becomes 1, and so it still works. X is still equal to a when t equals 0. Now the question becomes, if I start with something that's a little more generalized, I can take a derivative, and that's what I've done. I took one derivative to find the velocity as a function of time. And then when I combined everything together for the velocity, I want the cosine parts to drop out. So there's a gamma times a minus and a plus omega b. I want to just set those equal to each other. So this will work. What's going to happen at t equals 0 is that x is equal to a, v is equal to minus gamma a plus omega b. That can be solved by saying b is equal to gamma over omega times a. That will work. What will the new solutions look like? Well, there's a few more lines of algebra. I'm just going to jump ahead. If this is the solution we use instead for the displacement as a function of time, where we've added just a little bit of this sine function, we find out that at t equals 0, we're still at equal to a, but the velocity portion then goes away. At t equals 0, all I have is a sine function. I've eliminated the cosine components, and so we have the initial conditions that we were looking for. Now, what was gamma? And just a reminder that the gamma we're using is b, the damping constant, divided by 2 times the mass. So that's how that works. So, I went through this in a little more detail to show you what a more complete mathematical solution looks like. Don't worry about it. you can work from these formulas if you want, or you can go back and use the simpler examples. That's going to be just fine. Okay, let's ask this question. Now, if we put a lot of damping into this system, are we guaranteed that it will still oscillate? And it turns out it won't. It turns out that if you put a little bit of damping in, then you continue to get oscillations. But if you put more damping in, at some point the oscillations don't take place. Instead, if you put in what's called critical damping, then the object just returns back to equilibrium with an exponential approach. It asymptotically approaches equilibrium. If I put even more damping in, it slows that process down so that it takes even longer. So there's a set of solutions that correspond to picture A. Those are oscillatory, and those are referred to as underdamped. We have a relatively small amount of damping. B corresponds to what we call critically damped, and that means that we're going to return asymptotically back to equilibrium, and that's going to happen as quickly as possible. Now C is overdamped, and that means that we're going to head back to equilibrium, but it's going to take longer, just because of the damping system itself is slowing that process down. So it's kind of interesting that starting with the same equation, the same differential equation, predicts the existence of all three different types of damping effects. So all of those come out from the one differential equation. Again, you're not required to deal with all the math here. Now, the way we can determine if it's overdamped, underdamped, or critically damped, if the damping factor, B squared, is greater than 4mk, it is overdamped. And if B squared equals 4mk, it's critically damped. For oscillations to occur, B squared needs to be less than 4mk. That's how the categories separate out. So if we think back to the solution that they gave us, the frequency here being k over m minus b squared over 4m squared, what happens is we add more and more damping, the frequency slows down, and when the frequency hits 0, there's no more damping. So once b squared is equal to 4mk, this goes to 0, and we have to, we no longer have a frequency of oscillation. So that's one way to keep track of this condition that we're talking about. This is the condition that determines how the damping takes place. All right, so that makes it more realistic. Now, with damped harmonic motion, sometimes we want damping, sometimes we don't. Sometimes we want things to continue oscillating. The example they give here is like a spring inside a watch or a clock. If we have a suspension system, typically a suspension system, you want it to be critically damped or possibly overdamped. So if you hit a bump, you return back to equilibrium without all the oscillations taking place. What about earthquake protection? So this brings up the question of earthquakes. And here is here's an example of an earthquake, or on the right, and here's the Tacoma Narrows Bridge. Possibly you've seen that in some of your physical science classes, or you've seen this online or something. A bridge that was built outside Tacoma, Washington, that had a natural resonant frequency, and not long after it was built, a wind came up, a pretty strong wind, and was able to set the bridge into motion, and the whole bridge goes into oscillations. It's just remarkable People that were on the bridge, fortunately, everybody was able to get off, but the bridge, collapsed. And so that's an example of what we call forced oscillations. We can use an outside system to drive the oscillations of a mechanical system. And everything we build has some number of natural frequencies to it. If that object is driven, if it's oscillated at that frequency, then the amplitudes get larger and larger. Now the picture on the right, that's not far from here. That's just a couple miles from Laney College. That was the 880 freeway, Interstate 880, back in 1989 during the Loma Prieta earthquake. And here, the top, well, both layers of the double-decker freeway collapsed. So the upper layer collapsed to the lower, and the lower also collapsed. But you guys are probably too young to remember this. You've probably been taught this in classes, but this, at the time this earthquake happened, I was in graduate school, and I was driving to the Stanford Linear Accelerator Center. I was doing my research phase of my graduate work, and I was part of a collaboration doing particle physics research at the Stanford Linear Accelerator Center, and so I was driving back and forth on that freeway at least a few times each week. So when it collapsed, that certainly brought that close to home with something like that happening. All right, so let's go ahead and I think we're going to call that the end of the chapter. So that takes us through chapter 14. We're going to come back in chapter 15 and 16 and continue to look at oscillatory effects. Now, chapter 15 deals with waves. Chapter 16 deals with sound. And then once we're through chapter 16, that will take us all the way through what we consider to be mechanics. Mechanics has to do with forces and how they set up motion of objects. So the last four chapters, 17, 18, 19, 20, those are going to be thermodynamics, and that's going to have quite a different feel to it. So again, this chapter 14 has been we've looked at these things thoroughly. We're looking pretty good. Make sure you're looking at the homework problems yourself, and that will prepare us for chapters 15 and 16 very well. So any questions at all, stop by office hours, and let's get those looked at.